Generative AI has absolutely exploded onto the scene, right? It's doing incredible things, creating mind-blowing art, writing some seriously complex code, and honestly, it's on the verge of completely reshaping our digital world.
I mean, think about it. From the media we watch to the next generation of virtual and augmented reality, Gen AI is the engine driving what's next. It's not just replaying data, it's creating brand new things in a way that feels just as complex as the real world. Okay, but here's the catch. As these AI models get more and more powerful, they're starting to hit some serious walls. And these are walls that could actually stop things like next-gen VR or super-fast networks from ever really happening. This immense power, well, it comes with some equally immense challenges. So what are these problems exactly? Let's take a closer look at the growing pains that are holding generative AI back from its full, incredible potential.
Well, as these models get bigger, they become these absolute titans. Incredibly powerful, sure, but also super slow, rigid, and just wildly expensive to run. Take a model like DALL-E. It needs something like 12 billion parameters just to work. That level of complexity creates huge performance bottlenecks and makes it almost impossible for the AI to adapt on the fly.
So the big question is, how do we tame these titans? Well, researchers are coming up with two incredibly clever strategies. And it's not about just building bigger models, it's about building smarter ones. And the core idea is this. Instead of relying on one massive, single AI brain that tries to do everything, the future is all about creating these dynamic, collaborative teams of AIs that work together. Think of it like hiring a team of specialists instead of just one generalist.
Our first strategy is called Mixture of Experts, or MoE for short, and this one is all about achieving incredible efficiency through specialization.
So here's how it works. MoE acts like a highly efficient manager. It has this central gating mechanism that's kind of like a traffic cop. It sees a problem coming in and intelligently routes different parts of that problem to the perfect specialist for the job.
Just imagine an operating room, right? A complex surgery is needed. The head surgeon, that's our gating mechanism, doesn't do everything themselves. Nope. They direct the anesthesiologist, the heart specialist, and the nurses to each handle their specific roles. It's all coordinated, specialized, and super efficient.
And the outcome of this is a huge win for efficiency. Because you're only activating the experts you actually need, you save a massive amount of energy and computing power. You get faster processing, you get higher quality results because each expert is so focused, and it's all managed by that central coordinator to make sure you get a consistent, unified result.
But what about adaptability? I mean, efficiency is great, but sometimes you need flexibility. For that, we need a totally different approach. Let's look at our second architecture, the multi-agent system, or MAS.
Okay, so with this one, the key word you got to remember is autonomous. In a multi-agent system, you have multiple independent agents. They can all basically think for themselves, but they communicate and collaborate to solve a bigger problem. There's no single boss directing all the traffic.
A great way to think about this is a team of Mars rovers. Each one explores a different part of the planet, sensing the terrain and making its own calls. But, and this is the important part, they talk to each other. They share what they find to build one complete map of the entire planet. It's pure, decentralized teamwork in action. And the benefits here are just huge. This approach is incredibly adaptable. It's also really robust. If one rover breaks down, the whole mission isn't over. Plus, you get parallel processing and way more creative solutions because each agent can tackle the problem in its own unique way.
Okay, so let's just quickly put them side by side. MoE is centralized, with a boss assigning tasks to be as efficient as possible. MAS is decentralized teamwork, with autonomous agents collaborating to be as adaptable as possible. Two different strategies for two very different problems.
Now this is where it gets really cool. What happens when you combine the raw efficiency of MoE with the nimble adaptability of MAS? Let's look at a real-world case study, generating 3D objects for virtual reality. So here's the challenge. For VR and AR to feel truly real, we need to be able to create complex 3D objects in real time. But sending the massive amount of data you need to do that is a huge bottleneck. How do we get around that?
And this data point really just says it all. The research found that sending a bunch of 2D images to build a 3D object can take up to 20 megabytes of data. But generating the 3D model directly and just sending that, only 7 megabytes. That's nearly 3 times more efficient, a huge difference.
The solution they came up with is this beautiful hybrid system. They use a multi-agent system for the big picture coordination. But then, for the nitty-gritty specialized jobs, like picking the best images or optimizing the data transfer, each one of those agents uses its own mixture of experts. It is literally the best of both worlds.
And the results really do speak for themselves. You can see here how the system performed during its training. That combined MAS plus MoE system learns so much faster and just reaches a higher level of performance than the other methods they tested.
And the cost savings are just as obvious. Yeah, as the task gets more complex, the cost goes up for everybody. But the MAS plus MoE system is consistently and significantly cheaper to run than a standard greedy approach, which is just a method that doesn't delegate tasks as intelligently. So it's not only more efficient, it's also more cost-effective. So why is all this so important? This isn't just some academic thought experiment. This kind of breakthrough has really profound implications for the tech that we are all going to be using very, very soon. We're talking about the actual backbone of things like 6G networks, which need to handle just an insane amount of data. We're talking about making truly real-time, immersive VR and AR finally a reality. And this is the key to building the adaptive, autonomous systems we need for smart cities and self-driving cars. This stuff, it's the future. So it leaves us with this final fascinating question. When AI can work not just as a single giant brain, but as this coordinated team of efficient, adaptable experts, what are the truly massive, creative, and scientific challenges that we're finally going to be able to solve?